let me just say a few words, since I don't know who you are and where you are. Some figures might be insulting. Some of them might be novel. I don't know. So I made for the general public this presentation. So this is estrogen, the single chemical entity, the primary product of the ovary, which really activates the classical estrogen receptor pathways. And these are the physical chemical characteristics. The most important one is lipophilic, and therefore it's not bioavailable for oral administration. So this is a summary of what we believe estrogen is doing. So definitely it blocks menopausal symptoms, and these menopausal symptoms are complex. Hot flushes are the primary one. Then it prevents cognitive decline, although we just heard an hour ago that it might not be the case. It affects affective disorders. It has been reported beneficial effect in animal models of traumatic brain injury, spinal cord injury, Alzheimer's disease, myeloma multiplex, stroke, hypoxia, Parkinson's disease. But most of these data are, of course, based on rodent data, and most of them have not been confirmed in humans, although some of them were. So how estrogen is working, and this is just a summary from a group in Spain. As you see here, basically estrogen promotes stem cells and progenitor proliferation, that is neurogenesis, and in adult neurogenesis, primarily the hippocampus and olfactory bulb. Then it supports neurons and increases synaptic transmission and plasticity, and also, as I mentioned to you, it increases neuronal survival and neurogenesis in the adult. It acts on glial cells and control inflammation, and induces the release of different trophic factors, which are absolutely necessary for the normal brain function. Acting on oligodendrocytes increases their survival and myelination or remyelination, and it's important for MS. And of course, it has an action in the blood vessels. Primarily, it's a very potent activator of nitric oxide synthase, and nitric oxide is one of the most most efficacious vasodilator. This is just a summary of the estrogen action. That's the classical ER-mediated action when the two ERs are dimerized following binding to the ligand, and they regulate transcription of different genes. Then is this called tethered mechanism, which includes an activated ER, which then binds to transcription factors, and actually the transcription factors, like 81 or CFOS, will regulate gene expression. Then here is this non-genomic activation, the new membrane-associated estrogen receptor, which is responsible for the rapid action of estrogen acting through second messenger systems. Then there's a ligand-independent action of estrogen receptors, when growth factors actually phosphorylate estrogen receptors, and then after that estrogen receptors are dimerizing and then regulate transcription. And finally, I just added here, there is a receptor-independent action of estrogen, which actually might be very important. That is, estrogen is a very potent antioxidant because of the alpha ring in the molecules. A very few words, just the comparison of the two ER beta. What we just heard about, these studies were made by us long time ago. But here you can see the structure of ER alpha and ER beta, and then the localization of the message, the expression of these two receptors in one or two particular brain areas. What I just wanted to show you here, that there are certain regions which expresses both ER alpha and ER beta, but there are certain regions which express only one of them, like the olfactory bulb expresses only ER beta, or the paraventricular nucleus of the hypothalamus expresses ER beta, but the arcuate nucleus or the ventromedial hypothalamic nucleus expresses only ER alpha. A few images, just because I'm a morphologist and I like to see pictures. So estrogen receptors, of course, are nuclear receptors, so they are located in the nucleus. And you can see them here with a DAB staining and fluorescent labeling. These are ER beta in the paraventricular nucleus of the hypothalamus. This is the famous co-localization of GnRH and estrogen receptor beta. And then here is a figure from a group in Germany. They show, of course, these are tissue culture preparations. You can see a beautiful cytoplasmic ER alpha staining in green, a beautiful nuclear ER beta staining, and a membrane staining when they use this VSA conjugated estrogen as a ligand. So estrogen receptors are primarily in the nucleus, right? But this new receptor, of course, is associated with membranes. Now, that was my introduction, very short. Everybody remembers the WHI trials. 12 years ago, they published that those rosy eras are over. Estrogen is not as good as you believed. And it really, this publication changed the whole world, and I think we are still suffering from it. When you say negative data, everybody will remember them. If you see positive data, nobody will remember. So, what this publication actually reported is that there was a huge risk of taking estrogen and progestin together as far as the number of heart attacks, stroke, breast cancer, blood clots, and pulmonary embolism. And the only benefits effect actually were on colorectal cancer and hip fracture. And there was no action on the number of deaths and endometrial cancers. So when you see this, of course, it's very, very sad. As you know, a year later, they stopped the only estrogen arm of this study, which really showed not too much. I mean, there was nothing serious and there was nothing good. So they said, we know enough about it, so no reason to continue, waste the money. But definitely in the estrogen arm only, the beneficial effects were much, much prominent than the negative effects. So it looks like that progesterone, and particularly my feel is that the medroxyprogesterone here made something bad. So what we learned from the WHI studies? Again, this is a little bit different than what we just heard, but this is what actually physicians today believe and tell to the patients. Age matters. The length of hypoestrogenic period matters. That is, if you decide to take estrogen, take it as soon as your period is over. Type of estrogen taken matters. If possible, don't take oral estrogens like Premarin, because during conjugation, there are lots of toxic products are made, and that's actually the problem with the coagulation issues and pulmonary embolism. The type of progesterone matters. Probably MPA is not the best progesterone we can take. The good news for us is that we can still work on it. So what are the side effects of estrogen replacement therapy? Of course, some of those metabolites, the kinones, those are very aggressive and cause oxidative stress. Of course, we know that estrogen stimulates the uterus and the breast, and the orally taken estrogens like the Premarin cause the coagulation issues and thrombosis. So to antagonize, of course, these effects in humans, humans are taking progestins, either natural progesterone or still MPA. There's another way now to deliver estrogen through the skin or through the vagina. These are 17-beta estradiols and not Premarin, pregnant male urine extracts. But whatever you take estrogen, doesn't matter. You still have estrogen action in the breast and the uterus, what you'd like to avoid. So therefore, you would like to concentrate on the estrogen action on the brain, or the central nervous system, I would say. So, of course, the goal is to alleviate symptoms associated with estrogen deprivation in the brain, such as hot flushes, depression, cognitive deficits, neurological disorders, trauma, sleep disturbances. And at the same time, have a compound which have no uterotropic activity, and of course, will not have any effect on proliferation or malignancy in the peripheral tissues, primarily the breast and the abdomen and the endometrium. So, the first step was to develop selective estrogen receptor modulators in the dream that some of the estrogen ligand will function in the brain, but they will not function in the liver or somewhere else. And there was some, and there's still some very strong scientific evidence that such compounds actually exist, and some of them are here. The first was tamoxifen, then raloxifene and basoderoxifene. But basically, those which do not have any actions in the brain, that function almost like antagonists in the brain, right? But they have some beneficial effect in the periphery. But they cause hot flushes, depression, sleep disorders, just like castration. So it's not the best way to go. Then there was another effort to develop neuroserves, and they had these huge additions to the molecules and make them non-feminizing estrogens. Of course, these are not estrogenic anymore. But it turned out that actually, dose-dependently, they stimulate the uterus. So they were really not neuroserve. Then in the last couple of, I would say 2 decades or so, a tremendous effort turned toward, they called natural estrogens. I don't know why natural estrogen, because like genistein and diazine and S-equal, which are primarily ER beta selective ligands. And if you go to a pharmacy store or whatever, I mean, you can buy 2 tons of this, right? But unfortunately, they do not work. Although some people claim that they do, but you know, that's a psychological issue probably. So what we try to do now is to deliver estrogen specifically in the brain using a pro-drug approach. And this is indicated here. So my collaborator, Laszlo Prokai, who's a medicinal chemist, discovered that when estrogen scavenges free radicals, it turns indirectly to this compound. And based on this chemical name, and I'm not a chemist, it's dihydro, and it's that long, I just call it DHED, or paraquinol, not quinone, paraquinol of estrogen. And this compound, via a reductase, consuming NADPH, converts back to estrogen. When free radicals are still present, 17-beta estradiol turns to DHED. If the reductase is still there, there's a substrate, it goes to estrogen. So there's an intracellular redox cycle. And when you see this pathway, so that suggested to him that this compound can be served as a pro-drug, pro-estrogen. So today I'm going to talk about DHED. These are some of the physical-chemical characteristics of this compared to estrogen. As you see here, the lipophilicity is much lower, about a third. The water solubility, and this is critical, is extremely better. So this drug can be dissolved in water that is druggable, it can be orally available. And that's fantastic. Now, I don't know if who are familiar with this log p-value, but this guy, Hunch, described a long time ago a formula, and based on the size, the lipophilic, hydrophilic nature of a compound, he came up with this parabolic relationship between blood-brain barrier penetration and these numbers. And he said that if a compound has this log p value of 2, again, based on structure, lipophilic, and many other characteristics, it penetrates the blood-brain barrier very efficiently. And I'd just like to tell you, DHED is here. I think it's 1.87, but estrogen is here. So estrogen is more lipophilic than, of course, this compound. So it's almost optimal for blood-brain penetration. And we know that if you inject, and I will show you some data, if you inject an animal, within minutes, the compound is in the brain and not in the periphery. So this is again from Laszlo. What he did was he incubated brain homogenates with DHED, and at different time points measured estrogen with LCMS. And this is what he said. He treated these samples with DHED, and within 4 minutes, he got a peak for estrogen. If he treated uterus homogenates with DHED, he could not measure estrogen. So that just showed this fantastically rapid turnover of DHED to estrogen. Now when you use animals, and of course the first what we would like to know is no uterotropic activity, right? And it doesn't matter how long you treat the animal, how much DHED you give to the animals. You never see uterotropic activity compared to estrogen. So it really doesn't do anything in the periphery. So that is shortly DHED. So it's a fantastic opportunity to develop it as a drug because it's water soluble. It's not converted to estrogen in the periphery. It requires a brain selective reductase. So what I'd like to tell you now, what are the potential use of it and what we have done. with it. So this slide shows you that the female life expectancy is growing rapidly. And actually today it's even higher than here, right? And it also shows that women spend more and more and more years in the menopause in every decade. And as this figure shows, and again it's not absolutely updated, they spend as much time in the postmenopausal period as they spend in the reproductive period. So if you see this, this is a tremendous problem in the society, everywhere in the world, because they are suffering from hypoestrogenic symptoms. Maybe the monkeys do not, but women do. So what are these symptoms, of course? And I'm talking about primarily the CNS-related symptoms: hot flushes, depression, cognitive, neurological diseases, Alzheimer's, Parkinson's, sleep disturbances, as I mentioned before. So what I'd like to tell you now is how we study hot flushes and the effect of DHED on hot flushes. So these are the symptoms of the hot flush, right? So itchy, bitchy, very sleepy, bloated. You know, Gloria, I'm sorry, you know, right? So, and unfortunately, millions of women know. And believe me, they are suffering. So what is the mechanism of hot flush? We still don't know. But you know, we would like to know, and these studies go back to probably 30 years now, or 35 years, when somebody measured finger temperature very frequently. Actually, it was measured by conductors. And then FSH, LH levels, estrone and estradiol levels in the blood. And interestingly, whenever a woman reported a flush, and it was verified, the same time there was an LH peak. So that gave the impetus that maybe hot flushes are due to elevated LH. But we know that is not the case. How about maybe LH-RH, what you cannot measure in the periphery? But it turned out that it was the case. Although I still entertain this idea that the LH-RH, not the hypophysiotrophic which regulates anterior pituitary function, but the one which functions as a neurotransmitter, a neuromodulator, might play a role. So I don't know. So this shows you the cyclicity of a female during lifetime, during the reproductive period when you have cyclic changes of estradiol. Then you can see this perimenopausal period when the cyclicity is irregular, estrogen is up, estrogen is down, up again, down, and this is the problem. So it looks like not the absolute levels of estrogen are critical, because later on, women actually do not flush, although they do not have estrogen. So they adapt to it. But there's this critical period of changes, which can be 2 years or can be 15 years, right? So that's where we want to do something. So there is a theory by Friedman that basically what hot flushes basically are a response of the body to dissipate heat because the core body temperature, he says, is elevated. But it's not quite accepted by everybody. Usually core body temperature is not elevated. Okay? So it's not a real response. It's a false information to the thermoelectric center that the body is hot. So dissipate heat, right? That's normal. And what he said actually, that this thermoneutral zone within which you do not shiver, you do not flush, is narrowed down to a smaller scale in the menopausal women or perimenopausal women. And what estrogen does is actually restores this. Now, so what's happening here, I don't know, but I always like to prove this, that basically the thermoelectric center has thermosensitive neurons, right? It's like a thermostat. And I believe that in the lack of estrogen, the neurotransmitters which bombard these neurons via synaptic connections, right? The combustion is different. And that is translated as hot. And the response is dissipate heat. But I don't know, I mean, we suggested to do microdialysis and this kind of experiments, but the reviewers didn't like it. So, what are the current therapies for hot flush? Definitely estrogen. Estrogen blocks or prevent hot flushes. But since lots of women, particularly after the WHIR studies, do not want to take estrogens, so they try many, many different things. Progesterone actually works quite well, but make them sleepy and many other issues. Then SSRI, NRI the selective serotonin reuptake inhibitors or norepinephrine reuptake inhibitors, gabapentin, clonidine, and the soy products. I mean, all of these, they have some effect, but when you go to a clinical trial and you see the end of it, basically they are not over placebo. So, individually, yes, some women might say, okay, but as a whole, they do not do too much. So how to study hot flushes in rodents? Now you might say, rodents do not flush. That's true, and that's a problem. And so that's why we would need a primate model. And just before I came here, I submitted my application. We'll see with thermal imaging. So what we use is a pharmacological model, which is a morphine-dependent overactomized model. And in this model, if you measure tail skin temperature when you withdraw morphine with naloxone, you see this huge peak on tail skin temperature. And this is shown, actually that's the paradigm. So the animals are overactomized, treated with estrogen or DHED or saline. Then morphine pellets are implanted subcutaneously on day 8 and 10. And 3 days later, the morphine effect is withdrawn and the tail skin temperature is measured. Why tail skin temperature? Because rodents, particularly, actually I would say rats, regulate heat dissipation by the tail. Not too many species sweat. I don't know if you thought about this. Actually quite few. Horses, pigs, and I don't know. Is there anything else? I don't know. Rabbits use the ear, dog use the tongue, mice use the paw. Try to measure the temperature of the paw. I tried, sacrificed the ear and lost. So basically what you see here, the animals are now restrained, connected to this thermistor and the data acquisition system. When you give them naloxone, if the animals are overactomized, you see this huge increase in tail skin temperature. It lasts about 20 to 40 minutes. If you treat them with estrogen or DHED or ethinylestradiol, this action is much lower. So it's basically, whoops, what should I do? Press what?
No.
You have to connect it to the active power.
I'm sorry?
That's not, Okay,
What did I do wrong?
Nothing, you didn't do
No?
anything. All right.
Okay,
That
thank you.
should take care of it.
Thank you. So basically, this is the then the quantitative analysis of this. So basically, you see that estradiol, ethinylestradiol, and DHED at certain doses have a similar effect. We did a dose response curve following an oral administration of DHED now, and the doses were 10 micrograms, 30 micrograms, 100 micrograms, and as you see here, the 30 microgram was as efficacious as the 100, or we know that even higher doses did not provide a better response. So you might ask the question, why the dose of DHED is much lower, the efficacious dose of DHED than an estrogen? It's usually a 1/5 if you measure something like hot flush or depression or something like that. And it's probably because of the volume distribution. When you give DHED to an animal, all the DHED goes to the brain. You cannot measure it in the periphery. So all of them are concentrated in the brain, and estrogen, of course, is distributed all over the uterus, the breast, the liver, the fat, whatever, right? So that's probably the explanation. Why is it so efficacious? Then here we can, I will show you actually this one a little bit later in larger magnification, the effect of estrogen and DHED on these rhythmic changes, of diurnal changes of tail skin temperature. So you see an effect. It looks like estrogen, right? But you have to prove it. Now Laszlo now is measuring estrogen in the brain when I finished the experiments with LCMS. And I said, why don't we just select a few genes and measure the regulation of those genes when we killed animals after the experiments immediately, right? And we selected PR because we used PR when I was at Wyatt to screen estrogenic actions. It's so simple in situ hybridization stochasticity. And as you see in the preoptic area in overactomized animals, the expression is almost undetectable. It's there. but in estrogen-treated or DHED-treated animals, the expression is elevated, indicating that indeed DHED was translated to estrogen or transformed, and estrogen is responsible for this action. Now, how about the periphery? So we usually measure galanin expression in the pituitary because galanin is one of the most sensitive gene for estrogen. And as you see here, ethylene estradiol, as a positive control, stimulates galanin expression like 100-fold, but DHED does not stimulate it at all. And of course, we measure uterine weight or expression of C3 or PI in the uterus, and we cannot see anything. So, of course, the direct measurement is and pharmacological, morphine-dependent animal is always raised some flags. It's not physiological, so why don't we do something physiological? So we did a telemetric temperature measurements when we insert a thermistor subcutaneously, and this, the battery part is in the subscapular area or interscapular area, and then I tunnel this to the tail. So basically what we measure is temperature inside the skin, not over the skin. Okay, I try to put over the skin, but of course within 24 hours all the thermistors were chewed, and this is about $900 per piece, so you cannot use them. So of course that just shows that there's a telemetric, no connection, the animals are not restrained, the stress is not a factor, although stress is a very important factor for flushes. And this is based on these observations. In intact animals, you see this beautiful diurnal change in tail skin temperature, right, during the active or the inactive phase. And if you overactomize the animal, that change almost disappears. So again, if you give them estrogen, estrogen restores these changes. So we thought this would be a nice model again just to show that our DHED is indeed translated to estrogen. So this is what we did was overactomized animals, implant them with thermistors, then start recording for 2 weeks or whatever time, here's 2 weeks. Then treat them with DHE or estrogen or the vehicle for a couple of days, maybe a week, and then terminate the experiments, and this is what you will see. So in intact animals, the black, you see this beautiful diurnal change. If you overactimize an animal, no change. You give them DHED, but you can give them estrogen, doesn't matter. The changes are absolutely identical to those in intact animals. At this time point, we stop treating them with DHED, so now they are overactomized without hormone, and the diurnal changes disappear. So it's a nice model. These are not hot flushes, it's thermoregulation by estrogen. So now we change gears. We know estrogen is a female hormone, but we also know that estrogen is present in large quantities in us, right? And most of the testosterone in the brain particularly is aromatized to estrogen, and eventually the testosterone action is mediated by estrogen. So if that's the case, let's see, is hot flush an estrogen-mediated issue in males? And we know that it is, because if men are castrated due to prostate cancer, they flush like hell. What they do, they take ethylene estradiol for a while, then they start to have big boobs, and they stop. So estrogen works, alleviates hot flushes, but has the peripheral side effects, right? So here I'm showing you just one dose of ethylene estradiol. The grant will, if we got it, move forward and test DHED, but ethylene estradiol does exactly the same in a male orchidectomized than ethylene estradiol does in a female. So hot flushes are again estrogen-mediated events, right? So estrogen regulates thermoregulation even in the male brain. And again, just to show that indeed DHED transformed or translated to estrogen, I don't know what the best word to use, we just measured again PR expression in the male hypothalamus, and you can see is working the same way as it did in females. Here you can see a male animal, and this is the paradigm. So these are implanted by these telemetric transmitters, right? They are intact for a couple of days, then I castrate them, rhythmicity disappears, I give them estradiol, rhythmicity comes back. So again, thermoregulation, even in the male, is regulated by estrogen originating from testosterone. So this is a summary of the first part. I provided, I guess, evidence for a CNS selective beta estradiol. DHET is similar to estrogen, lower tail skin temperature rise induced by morphine withdrawal, and does affect diurnal changes in temperature. So it looks like the hot flush area is an area when it really has potentials. How about depression and anxiety? And these were collaboration with Todd Gold's group in our university. And what they did was they evaluated antidepressant-like effect of estrogen and anxiotic-like effect of estrogen using different paradigms such as forced swim test, tail suspension test, learned helplessness test, elevated plasmase, open field. These are very sophisticated experiments, fun to watch, and this is what the result shows. Forced swim test for depression. This y-axis indicates you the immobility time the animal, these are mice, spent floating on the water. And of course, the shorter the time, the less depressed the individual is. And as you see here, DHED at 3 microgram per kilogram has a better effect than estradiol at 25 microgram per kilogram. Again, I'm referring to the volume distribution. There's another test called tail suspension test. Again, the immobility time is indicated on the y-axis. As you see here, DHED at this low dose has the same effect as estrogen on this particular assay. Open field, it just shows you at first that the activity is not changed, not affected by estrogen or DHED, so it's not a confounder. But when you see here, the animals spend more time in the center lines to explore, to learn what's going on down there. So they are not as anxiotic. And there's another one, elevated plasmase. Again, they spend more time on the open arm to explore, and a similar effect can be seen following estrogen and DHED treatment. Whoops, this way. So I just summarize what I just showed you. I don't have to read it again. Now let's go to sleep disturbances. And now Jessica Monks is coming. So what she did was, she has again this telemetric system from PSI, and what she found actually that similar to estrogen, DHED reduces the REM sleep time. Okay, not the non-REM, but the REM sleep time. And we know that estrogen is really help to spend a good night, and the sleep pattern will be more pleasant than without estrogen. How about stroke? You know, many studies showed in rats and mice and what is the species which doesn't have the complete circle of Willis? Gerbils.
Oh, sure.
That estrogen is protective from hypoxia, either representing a stroke or a heart attack or something like that. And here you can see 3 columns, control animals, estrogen-treated animals, and DHED-treated animals. And the white area represents the area which is dead. It does not retain this pain when you have these 1 millimeter sections. So you see here, estrogen provides quite a nice protection. Only the certain superficial cortical areas are dead, and DHED does the same. But again, 20 microgram of DHED can provide the same results as 200 microgram per estrogen. Okay, so again, volume distribution, and it's indicated right here, right? So it's really has a tremendous advantage to estrogen. Okay, and that's the summary. Now, effect again on the periphery. So we would like to avoid any peripheral actions, right? Uterus, breast, pituitary. And here you can see mRNA level was 3,3, complement 3 in the uterus. It's not stimulated by DHED, contrary to estrogen. mRNA for ghrelin, I already showed you, not stimulated. And here is an image what I show, and this was made by collaboration with Angelo Brody's group, when they had this MCF7 tumor cell lines which are transfected with aromatase, and then they have this luciferase construct, right? It's a transactivational assay. So if you have a ligand, androstenedione is the precursor for estrogen. and aromatase changes it to estrogen, then you can see a huge transactivation. If you just give them estrogen itself, it does the same. It's almost the same, right? I'm going to learn it later. They should be different, but the fact is there. But if you give them DHED, there's no transactivation here alpha at all. Now, then later on, we did another experiment. And then we inoculated tumors to nude mice. And these cells which were inoculated, again, they have the aromatase enzyme, okay? And so inoculate the mice, wait 3-4 weeks until the tumor tried to go, and then at certain size, I think it was 300 cubic millimeter, they were treated from the beginning with this precursor for aromatase, androstenedione, okay, which is translated then to estrogen, or vehicle or DHED. But after, I think it was 1 or 2 weeks, this group were split into 3. One remained the same, treated with the precursor, another one was treated with vehicle, and another one was treated with DHED. So what do you expect? Of course, these cells try to grow, and these cells will not grow. And this is what you will see, right there. So this is the split. This is the split right here, right? So the cells grow when they treated with the aromatase substrate. These are the controls with the vehicle. And as you see, when they start to be treated following the initial treatment with the substrate, right? This now is 6 weeks now. DHED start to slow down the growth, but definitely it not stimulates significantly. So again, showing that in this in vivo paradigm, it has no effect on the breast. Now it's not easy to measure or weigh breast tissue in mice, but I really try to see something in vivo histologically or in situ hybridization or something like that to see what's going on in vivo in these mice. Maybe you have to go to rats. So, no effect on the uterus, no effect on the pituitary, no effect in the breast. Perfect. So how about DHED in men? I already showed you the hot flush model on male rats, right? It worked. But this is just an introduction why it would be interesting to have a ligand like this and treat castrated or even naturally aging men in the andropause, because they have these issues, right? They have hot flushes, learning and memory is impaired, they have the same depression, anxiety, probably that's the second most critical one, and they have some issues with learning and memory. Again, the monkey studies didn't support this. So it's very interesting. So, estrogen can do this, but of course, ERT causes gynecomastia and thromboembolism or pulmonary embolism. So, that's where we are. These are some of the collaborators. The idea came from this guy, the intracellular redox cycle and proestrogen as a delivery system to take this compound to the brain. And the wife is a chemist who is making the compound, and these are the guys who are making the experiments. Thank you. Any questions?
Where do we get it?
Pardon?
Where do we get it?
You know, those women who know I'm working on it, when I meet them on the hallway, do they have it? I said, I get some, but I cannot give it to you.
So one of the you may have seen the paper that came out of Canada many years ago, giving estradiol in moderately high amounts, along with an ER alpha antagonist that couldn't cross the blood-brain barrier. So in that way, it was wonderful for the brain that it blocked all peripheral activity except bone.
Yes, yes.
What does this do to bone? Can you get it? It doesn't help bone.
Nothing.
So we still need a drug.
You still
to make
need
our
something to
bones
maintain
work.
your good bone. But there are so
But
many.
that's what
I mean, there are so
things
many.
out there.
Yeah, sure. I mean, biphosphonates and PT. I mean, there
Yeah.
are so many others.
Yeah.
Yeah. But yeah, I'm familiar. Actually, when I was Wyatt, we were working on this.
Yeah.
So combining
But that
basodarcetane and
never
others.
happened. Yeah. What happened to the field?
I don't know. Is it practical or I mean, I don't know why, but
Yeah.
it works. It should work,
Yeah.
right? It should work.
Yeah.
It should work.
It sounded good to me.
But still, you have some other,
Yeah.
issues. Yes.
So what about cognition?
We don't have, you know, these, Todd Gold is involved in this studies, who's a behavior neuroscientist, and he would like to do this experiment, but right now, as we speak, we ran out the R01s and did not get the humans, so we are a little bit slowed down. It's too bad because this compound is so important. But you know, when you submit a grant on DHED to treat castrate men, probably in the introduction you describe why. What's the first question of the reviewers? Do you want to treat a man with estrogen? Then what? I mean, then what?
I mean, they don't realize that a lot of the brain effects of testosterone are estrogenic. So, you know,
yes.
come on.
Could you please show me again the structure of DHED?
Yes.
I am a chemist. Okay.
You should be a chemist. That's what I would say. You should be a chemist. Now, don't ask me, please, any details, because I know that aromatic ring, probably that's it. No, anything more.
No.
Okay, we are almost. Okay, one more. Right.
Yeah. So, is this compound absolutely stable?
I'm sorry?
Is this compound DHED stable?
Yes. Oh yeah. Absolutely. I keep it on room temperature. I have one which I'm using for 3-4 years.
On the bench?
On the bench.
No
I
problem.
mean, dry, dry. I'm keeping dry. That's it. Yes. And actually, we have compounds we dissolved in a very, very small amount of DMSO, but very, and saline. And I kept it for, I don't know, a year, and used it just for fun. That it's still working. I mean, do you see any structure? You know, I have no idea about chemistry. Okay, so is there anything which would suggest no? I don't know.
Yes, because you see this hydroxyl group and the ring junction here.
Yes.
In the AD ring.
Yes.
That's a strange hydroxyl group.
Yes, that's strange. Oh.
Yeah, it's for me. So, but I think you can answer.
Yeah. Unfortunately.
Do you know, just another question, do you know, it's a long synthesis to make this compound? It's a long synthesis, have you an idea? The chemist starts from estradiol or estradiol?
I don't know, I just know that when I need compound, my friend always tells me, you know how long time does it take to make it? But
okay.
I don't.
Okay.
You're saying in the body that goes from estradiol to DHED?
I think that is an intermediate, actually. It should be an intermediate. Am I right? Here. Estradiol, right, somewhere here.
Yes,
there should be an intermediate.
That's why I asked you the question.
Yeah.
Does the chemist start from estradiol?
Actually, I had another figure which showed this intermediate. I don't know why it's not, because I asked him to show the circle for me, the cycle.
Okay.
Because I explained the cycle, but I did not show.
Okay.
So that there was an arrow here, a compound, and that.
Okay.
So then you can see the cycle.
Okay.
Yeah.
Okay. Thank you.
Yes.
In your introduction, you mentioned that estrogen acts through 3 ways, binds to the receptor inside.
Yes.
Do you know whether these 3 different types of mechanism are restricted to particular tissues or particular time, or where they act? 3 ways of mechanism.
You know, I'm more familiar with, of course, the central nervous system, and both the classic transcription factor like activity alpha, beta, and the membrane called GR30. Those are existing in neurons, neuronal cells, whatever. You know, I'm not sure whether the membrane associated is in the uterus. Honestly, I'm supposed to know it, but right now I just cannot recall any specific.
I don't know of anything. I haven't looked.
Yeah.
But somewhere
I would be surprised if not. Honestly, I would be surprised if not.
You are especially the third one where the membrane one and then growth factor.
Yes.
I have
That's definitely present in the uterus.
Yeah,
For cancer issues, yes.
Yeah,
For lab, yeah.
My second question is, now you have done really exemplary work with the DHED in the mouse model, in the rodent. in the rat model. But from the other speakers and all, rat is really not a good model to represent the human, and especially with the DRIP and androsterone, it's shown that rat is not a model to rely on. So what I'm asking is how you are going to take it to another level where you can see, yes, it can work in human. So what other plan you have to prove that?
So what we are doing right now is bombard NIH for grants to have primate models. A primate model for Harfouch, and I just submitted, as I mentioned today, that I came in before I came here. And it had a good review, but one reviewer totally misunderstood. And you know, my collaborator published a paper in about 10 years ago, I think in 2002, when he criticized one of his pro-drug approach, which was claimed to be the clear one, right? So they repeated, and it turned out, no, it was uterotropic. And you know, he was a chemist, he knew what the problem was. So he published this paper. So you see the third reviewer after number 1 and number 2, every question, every number is 1, 2, 1, 1, 1, 1. This guy's 7. And he starts, by the way, your future collaborator, I mean, Laszlo, my colleague, is not in this monkey paper because this is to develop a monkey model with estrogen. And once we have it, then take PHED to the monkey model, right? So he's not there. But in that future direction, you mentioned that this is why personally I want to develop it. Because we have this compound in our hand, right? Says, by the way, your colleague just published that is an absolutely stupid idea, it doesn't work, so what do you want? Yes, it's in, that's the review. That's the review. And then I called the program officer, cool down, sleep for 2, don't make enemies, answer the question. But, you know, so, then of course, if we have the monkey model, we actually working right now with a group in Emory to study DHED on sexual behavior of monkeys, but I don't know the results of it. But then we would like to expand this to other models and eventually file an IND. But we need toxicology studies. Now that's about $1 million, right?
Yeah.
Who will pay for it? NIH will not. So, you know, I mean, Laszlo has a small company called Virtual Company, so we probably are looking for investors to give us money to do a toxicology study, and then we can file an IND, and then who knows? Yes.
Yeah, nice talk. I enjoyed, though I don't understand certain aspects, so
Yes.
I will ask you a question. I'm not a chemist. Simply, I don't understand how you can get from the red molecule, the black molecule, how you can lose the OH group, this reductase.
Right here.
Exactly.
Right here.
Yeah, that's really amazing.
Guys, honestly, I don't
You
know.
don't know.
I can ask him.
Okay.
That I had this question.
Okay.
I don't know.
So if you don't know, you don't.
No, I don't. I'm not a chemist.
Yeah, yeah.
But you are welcome to contact him. Why not?
Uh,
But I can ask this question, and if you don't mind,
Okay.
and if you send me an email, I will respond.
Okay. The other question: for how long the black molecule stays in this configuration?
That's one.
This one. You know, this reminds me. No. Why I'm asking?
Yes.
Are your effects really due to changes of the black molecule to the blue molecule to estradiol, or is it the effect of the molecule, the black molecule itself? It reminds me neurosteroids that are always charged, or part of them are charged at the carbon C3, and this molecule is also charged at the C3 carbon.
C3.
Yeah,
minus.
there is O minus. So I would predict that this molecule may have some, let's say, stimulatory effect on NMD receptors, which may appear to have some neuroprotective effect or something like what you see. You can, by changes of the activity by NMD receptors, have number of other effects. The neuroprotective effect you see is typical for inhibitors of NMDA receptors. I will talk about this tomorrow. I'm not quite sure whether, you know, you certainly have an effect, but I'm not quite sure whether the explanation you provide is the one that is
So
correct.
you might believe that actually this guy is doing something.
Yes,
What
exactly.
we are measuring.
Yeah, exactly.
I will ask him. Honestly, I don't know.
Sorry.
No, it's okay. I appreciate that.
Yes, but neurosteroids are not aromatic.
Oh, no. Okay.
Okay.
Oh, so
Sorry.
this is aromatic. That's aromatic.
Pregnenolone sulfate has also double bond and has sort of flat structure.
Yes,
So
but it's not aromatic.
Not aromatic, but I have in my collection of compounds that we tested aromatic, similar to estradiol, and they act on NMD receptors for sure. I know them.
Oh, it's very, on a chemical point of view, it's very interesting, your transformation.
I see.
And it's very interesting how the chemists get this compound.
I see.
It's really interesting.
I just received by
No,
yes.
it's,
So have you measured
Yes.
estradiol in the brain after
Yes.
PhD?
So exactly. And you know, I didn't show it, but I can tell you that we discussed this in the light of endogenous production of estrogen in the brain, right? How you can rule out that what you see is not endogenous estrogen. So what he did was during the synthesis, he used, I don't know how to pronounce, deuterium? Or
deuterium, yes.
Deuterium, right?
Yeah, right.
So deuterium labeled DHED, and when he measured 70-meter estradiol, the deuterium was there. So it doesn't come from cholesterol or whatever, right?
Yeah,
it's coming from the substrate.
Yeah. Absolutely.
Yeah. I'm sorry, what was the question? I'm sorry. What was your question?
So you have measured the
Yes, estrogen. So he
levels
measures
in the brain.
estrogen. Yes.
Why doesn't it go up in the uterus preparation? Because there's no reductase there?
No, that is. Yeah.
So does it increase estradiol everywhere in the brain, or is that rigid? I mean, it's
Well, you know, he started to measure estrogen in a larger amount of brain, and then narrowed down, as far as I think his sensitivity allowed him to measure. So now he goes back to like hypothalamus and can measure, or hippocampus, whatever, right? And when he makes this big dissection like cortex, frontal cortex, hippocampus, amygdala, basically there is not that much difference among, which means that maybe this reductase is a brain selective but non-region selective. I mean, it would be nice, you know. I always ask him because my interest is a bit different, right? I mean, each of us want to have a treatment for menopausal hot flushes. I mean, reductase, why don't we clone this reductase? I like to see where it is. I'm a morphologist. I mean, can you imagine a big show? Who cares? Who will pay for it? It works.
So Andrew, make some. Clone it.
Oh, clone it if you can clone it. Yeah.
Not a protein.
And he does beautiful
Proteomics?
proteolysis of this, yeah. But I didn't show any of this because that's really not my area. So